Ever feel like you're drowning in data, trying to piece together the puzzle of what it all means? Today, we're handing you a powerful shortcut. Welcome to the deep dive, where we take the sources you've shared and extract the insights that truly matter. Consider this your direct route through the essential information, aimed at those crucial aha moments without overwhelming you with unnecessary detail.
Yeah, and for this session, the material you provided really digs into the fundamentals of how we structure and interact with data. We're
Okay.
talking about data modeling, those critical database joins, optimizing SQL performance, which is always a big one, and ways to connect different data sources.
Exactly. And our mission is pretty straightforward. We want to shed light on the core principles of database design and manipulation, focusing on efficiency and helping you avoid those common pitfalls that can cause some real headaches down the road. Okay, let's dive right in. Let's talk about the very foundation, modeling our data.
Right. So the initial phase, really, of any database design is identifying the core entities, the fundamental things we need to track and understand. But what's interesting, and what the sources highlight, is figuring out the difference between what might seem like a key entity and what really functions as a main entity, the one driving the whole structure.
Right. So in the discussions, there's a good example. These code-like key entities, like beginner, intermediate, advanced for course levels. You might instinctively think, okay, key categories. But the discussion points out we don't necessarily rush to create separate tables for those right away. Why hold back initially?
Well, it's mainly about keeping things clear and manageable early on. Avoid unnecessary complexity. The first goal should really be establishing the essential framework. The transcripts bring up this idea of dependency. Like, if a subject, say, a course level being advanced, directly dictates an object,
Hmm.
maybe the availability of intro courses, then it might become its own entity later. But it's not automatic.
And that's different from things like equipment, right? Like pumps. Sure, a pump can be centrifugal or submersible, but the type itself isn't necessarily the main entity dictating everything else in the core model.
Precisely. And the material mentions a really crucial concept here,
Mm.
the semantic subject.
Mm.
Think of it as an entity that's like a central pillar. It fundamentally shapes how other related things exist and what attributes they have. Take process control parameters. If those parameters are tied directly to the equipment type, like all motors of Model X need the same settings, then that type becomes a pretty significant semantic subject.
Ah, okay. But if the parameters are specific to each individual motor, even if they're the same model, then basing the model just on the type could mean tons of repetition, right? Setting up the same parameters for like 100 identical motors. That sounds like a complexity nightmare.
Exactly what you want to avoid. And what's interesting is how pulling out these non-key entities too early can actually muddy the waters. It can obscure the really important relationships you're trying to pin down in the core model. Adds noise.
There's a great analogy in the transcripts for this Napoleon's father. The point isn't his own fame or wealth, but his fundamental link to Napoleon. So the insight is prioritize entities based on their relational influence, not just how important they seem outside the database.
You got it. Don't just toss an entity aside without understanding how it might connect to or generate other related information, its influence on the bigger picture. There's also a mention of the Korean phrase, jene, which is roughly like seeing with knowledge or understanding through examples. It just highlights how helpful concrete illustrations can be, especially when you're trying to explain these sometimes abstract entity relationships to people who aren't deep in the technical details.
Wow.
Experience helps, but examples really bridge the gap.
Speaking of examples, that student instructor attendee one is really good. How you define student initially matters a lot. Like, is an attendee automatically a student? Maybe they're just auditing. These simple terms can have big implications for the database design. Is it an entity or just a relationship or an attribute?
Yeah, and the idea of a constituent comes up as a way to potentially unify roles, like student, teacher, attendee. Instead of separate entities, maybe one constituent entity with a role attribute. This helps avoid duplicating data and inconsistencies, which is a huge risk if roles aren't properly defined and integrated. And that integration isn't just physically merging tables, it's about logical coherence, making sure it all makes sense together.
So the big picture goal is simplifying complex business stuff through good modeling. And the transcripts stress that things change in the real world, right? So the model needs to evolve too. It's not set in stone.
Absolutely. It's iterative. And it's so important to get this foundational understanding of entities nailed down before you start drawing diagrams. The sources also point out that typically your key or main entities are a smaller group compared to all the action or event entities you might track. That helps narrow the focus initially.
And these decisions about key and main entities, they're pretty critical, aren't they? Hard to undo later. They really form the skeleton of the database. The analogy used is like prepping your essential building materials. You absolutely want to get that foundation right first time. Okay, so we've got our key entities sorted. What's the next step in the design?
Well, that naturally leads us into defining the relationships between these entities, the connections, the joints that link them all together. The transcripts make a good point that while you could potentially draw lines between almost any two entities, only a fraction of those possible relationships are actually relevant and needed for what you're trying to achieve.
Like the steel beams in a building analogy, right? You could connect them in endless ways, but you only make the specific connections needed for a stable structure. We need to get beyond just guessing here.
Definitely need to move beyond trial and error. And a core idea is that any relationship is bidirectional. You've got the relationship from A to B, but you also must consider the relationship from B back to A. The transcripts talk about three perspectives: A looking at B, B looking at A, and sort of an outsider's view.
That couple walking down the street example illustrates that well. An observer might assume something, but it's just an assumption. We need objective ways to define these links in our data.
Exactly. So the process involves taking one instance, just one example of an entity, and figuring out its connection to the other entity. Then, critically, you flip it around and do the same from the other entity's perspective. Let's use the classic employee and department relationship. People often jump to, oh, that's one-to-many.
Yeah, seems simple enough.
But the transcripts break it down really nicely, that one-to-many is actually a combination of two separate perspectives. First, the relationship from one employee to their department. Second, the relationship from one department to its employees.
Okay, got it. Two sides to the coin.
Right. And focusing on the one side first. A single instance of anything is always, well, one. One employee is one employee. The tricky part is determining the cardinality, the number on the other side. Is it one or is it many? And the transcript suggests using proof by contradiction. Reductio ad absurdum.
Okay. The prove me wrong method. If you can find just one single case that violates a one relationship, then it absolutely has to be many.
Precisely. So you ask the users, can you show me any evidence that disproves this is a one relationship? For instance, can any employee belong to more than one department at the exact same time? And clarifying that time aspect, current versus historical, is crucial. You need precise definitions.
Absolutely. Ambiguity there could lead to big problems.
Then the discussion moves into the must-have versus can-have aspect, mandatory versus optional relationships. You see these as solid versus dashed lines on diagrams. Think parent and child entities. Usually a child record can't exist in the database without its parent record being there. It's mandatory.
Which is vital for data integrity, right? Avoids those orphan records, bits of data floating around unconnected.
Totally. And sometimes you might find the business rules actually need tweaking to enforce these mandatory links. Like maybe even temporary staff must be assigned to some department, even a temporary holding one. It shows modeling isn't just passive. It can drive process improvements.
So it's about guiding towards objective decisions, not just finding what's already there.
Exactly. So a well-formed statement for our example might be, each employee must belong to one and only one current department. See how specific that is.
Yeah, must for mandatory, one and only one for cardinality, and current for the time aspect. Clear. Okay, now flip it. Department to employee.
Right. Does a department have to have employees? Well, think about setting up a brand new department, maybe for product planning. It might exist on paper, in the system, before anyone is actually assigned to it. So a department can exist without employees initially. That makes the relationship optional from the department's side.
Okay, so putting it all together. Employee to department is mandatory one-to-many. Department to employee is optional one-to-many. And that translates to the diagram notation, like the crow's foot.
Exactly. You synthesize those two carefully analyzed perspectives into the final representation. It seems simple, but doing this rigorously avoids so many downstream issues.
It does sound thorough, and I can see how skipping this careful definition could cause chaos later.
For sure. And if you're thinking, wow, that sounds like a lot of work for every single relationship, the transcripts do acknowledge that. They suggest prioritizing. Focus this intense effort on the really critical relationships first, the ones that form the backbone of your system.
Makes sense. And naming conventions.
Be specific. Currently assigned to is way better than just belongs to. And the convention usually is the one side entity kind of gives its key as a foreign key, and the many side receives it.
Gotcha. And different diagram styles exist, but consistency is key. Understand your chosen notation like crow's foot for many, single line for one, solid for must, dashed for can.
Yep. So now we have entities and relationships defined. How do we actually pull data together when we need it?
This is where it gets interesting, moving beyond just joins. The sources talk about set operations, specifically union all, as a really useful alternative sometimes, especially for what they call radial data models, like a central master table with several independent child tables branching off.
Yeah, exactly. Think of an account master table. Then you have a separate deposits table and a separate withdrawals table. The challenge comes when you want a single list showing both deposits and withdrawals together. They're in different tables, and there's usually no direct link between a specific deposit record and a specific withdrawal record.
Right. Trying to join deposits directly to withdrawals doesn't usually make sense. And using outer joins to the account master can get complicated if you want everything nicely interleaved by date, for example.
And just querying each table separately for the whole time period and sticking the results together manually, often very inefficient. So the transcripts introduce union all, but with a clever twist, adding strategic dummy columns.
Okay, explain the dummy columns. How does that work? And how is union all different from a join here?
Well, think of union all as fundamentally about addition. It just stacks rows from one query result on top of another. A join is more like multiplication. It creates combinations of rows based on matching keys, which can sometimes inflate row counts unexpectedly in one-to-many scenarios.
Yeah.
Union all avoids that inflation when you're just trying to combine similar types of information from different places.
Okay, addition versus multiplication. Makes sense. So good for combining things from different branches of that radial model.
Perfect for that.
Mm.
It's also great for many-to-many situations or where data is asymmetrical. Like, imagine a goals table and an actual results table. Not every goal might have a result yet, and maybe some results aren't tied to a specific goal. Direct joins can mess up your totals in cases like that. Union all handles these gaps more naturally, often without needing full outer joins, which, let's be honest, aren't supported the same way everywhere.
So back to the dummy columns with deposits and withdrawals. How does that work practically?
Okay, so when you query the deposits table, you select the deposit amount, date, account ID, etc., and you add an extra column, maybe call it withdrawal amount, and just put a 0 or NDL in it for every deposit row. Then you do the opposite for the withdrawals table. Select the withdrawal amount, date, ID, etc., and add a dummy deposit amount column with 0 or NLL. Finally, you use union all to combine the results of those two select statements.
Ah, I see. So you end up with one big list where each row is either a deposit or a withdrawal, and the column for the other transaction type just has a 0 or null.
Exactly. Now you have a unified data set you could easily group by account, date, whatever, and test the deposit and withdrawal columns correctly.
Clever. Is there a preference between 0 and NLL for those dummy values?
The transcripts suggest being a bit careful with NEL for numeric dummies. Sometimes aggregate functions like SEM might ignore NELs in ways you don't expect. Using 0 is often safer and more predictable for numeric placeholders. Another example they give is a master table, maybe with product info, and then separate tables for local currency prices and foreign currency prices. Union all with dummy columns works beautifully there too.
And you have to make sure the columns line up perfectly in the union all, right? Same number of columns, compatible data types.
Absolutely critical. The number, order, and data types must match. The transcripts even mention a little trick. Using functions like toNumber, NO, if you need to create a numeric dummy column but don't have a 0 value handy, just to ensure the data type matches the corresponding column in the other select.
Okay. And what about performance with union all? Any pitfalls?
A key principle mentioned is unifying at the lowest common denominator. Avoid doing complex calculations or conversions inside the select statements before the union all, if you can help it. Why? Because it can stop the database optimizer from using indexes effectively on the original tables.
The example?
Say you have monthly sales targets, but daily actual sales data. You want to combine them. Don't try to aggregate the daily sales up to monthly within the select statement that feeds the union all. That calculation might prevent the database from using an index on the daily sales date column. Better to union all the daily sales with dummy target columns and the monthly targets with dummy sales columns, maybe distributing the monthly target across dummy daily rows if needed, or keeping it as is, and then do the monthly aggregation in an outer query after the union all.
Got it. Keep the initial selects simple for indexing, do the heavy lifting after the union.
Precisely. And the really complex profit and loss by business unit example shows this power. You union all data from revenue, cost of goods sold, indirect costs, etc., all with carefully placed dummy columns, and then perform the necessary calculations afterwards to build the final P&L report. It's a very flexible technique.
Okay, structure, combining data. Now, performance tuning. The classic challenge.
Right. And the transcripts offer a really good concrete example. A developer was struggling with a SQL query, taking ages, reading tons of database blocks, classic symptoms.
What was the problem?
Looking at the execution plan, the inefficient query was starting with a join that wasn't very selective. It joined large tables together early on and only applied the most restrictive filter, based on something called a node group name, much later. This created a huge intermediate result set that the database had to chew through, even if the final output was small.
And why did the database choose that inefficient path?
Well, the key insight, and a common misunderstanding the transcripts point out, relates to inline views or subqueries. The developer might have thought writing the most selective part in an interview would force it to run first.
But that's not always how it works, is it?
Nope. The database optimizer makes the final call. It looks at statistics, indexes, the whole query, and decides what it thinks is the best order, which might ignore the syntactical order you wrote it in. And indexing played a role here too. There was an index on one table, stream, that was probably useful for other queries, but for this specific query, the optimizer latched onto it early, and it led down an inefficient path.
So the index wasn't inherently bad, just bad for this query's execution plan.
Exactly, which highlights why indexing strategy is so nuanced.
So what was the fix?
Dramatically simple, actually, adding an ordered hint to the query. This hint basically tells the optimizer, hey, execute the joins in the exact order the tables appear in the from clause. It overrode the optimizer's less than ideal plan.
And the result?
Huge improvement. The optimized query, which is also simplified a bit structurally and used a nested loops hint, ran much, much faster and read drastically fewer database blocks.
That's a powerful demonstration. Any visual clues in the plan?
The transcripts mention looking at SQL traces. Ideally, as you go through the steps of the execution plan, the number of rows being processed should generally decrease as filters and selective joins are applied. Wild fluctuations, especially big increases in row counts mid-plan, often signal a problem like the one described. It really boils down to understanding indexing and how the optimizer thinks. That ordered hint was like giving the optimizer a crucial piece of missing context for this specific query.
Okay, so optimizing existing queries is key. What about writing smarter SQL from the start? Any advanced techniques discussed?
Yes, there's a neat one for generating summary rows like totals or subtotals within a single query result, without needing multiple queries or complex procedural logic.
Oh, like adding a grand total row at the bottom of a report? How's that done in one go?
Okay, imagine a simple data set. A100, B100, C50. Goal. Add a row at the end saying total equal 250. The technique described involves creating a tiny dummy set of data, maybe just a temporary table or inline view with two rows, values 1 and 2. You then cross-join your original data, A, B, C, with this dummy set. This duplicates your original rows. Now you have one set tagged with 1 and another tagged with 2.
Okay, so double the data. Then what?
Then comes the clever part. Conditional grouping. Using something like decode or case, you tell the query, if the dummy value is 1, group by the actual columns, A, B, C. But TI if the dummy value is 2, group by a constant literal string like total.
Aha. So all the rows tagged with 2 get lumped into one group called total.
Exactly. And then you can use aggregate functions like SUM on that total group to get your summary calculation, 250 in this case. The rows tagged with 1 just pass through, grouped by their original values.
That's pretty cool. Avoids a separate query just for the total.
For sure. And the transcripts share a funny story about a developer trying to get a total by country row at the bottom and using really complex string manipulation just to force the sorting.
Oh dear. There had to be a better way.
Yeah, the conditional grouping method is much cleaner. You just use a constant for the total rows grouping key that naturally sorts last, like maybe ZZZ or sometimes NLL, handled correctly in the order by Y.
Could you put the total at the top instead?
Yep, just flip the logic in the conditional grouping and sorting. Use a grouping key that sorts first, like arable A or maybe an empty string. The transcripts also give a nod to more modern SQL features like rollup and QoE, which are built-in extensions in Oracle and other databases specifically designed to generate these kinds of subtotals and grand totals automatically within a groupie by Y clause.
Right, so databases have evolved to handle this directly now too. Good to know both techniques.
Definitely. Being aware of these advanced SQL features can save a lot of time and lead to much more efficient queries compared to trying to build the same logic manually or through multiple passes.
Okay, let's try and wrap this up. We've covered a lot of ground.
We really have.
Yeah.
To quickly recap, We looked at how crucial that initial entity and relationship modeling is. Getting that foundation right is paramount for efficient databases.
Hmm.
We explored when to use traditional joins versus the set operation union all, especially for combining data from different sort of parallel sources. Both have their place. And we saw how SQL query structure, hints, and especially indexing can have a massive impact on performance, sometimes in surprising ways.
Absolutely. So here's a final thought for you, the learner, to chew on. Understanding these underlying database principles, it isn't just about tech specs. It's really about understanding how information itself connects, how it flows. It makes you wonder what other deep dives into seemingly technical topics might actually reveal surprising insights about the world around us. We definitely encourage you to keep exploring these concepts. Think about how they apply to your own challenges when you're working with information. Thanks so much for joining us for this deep dive.